Alright, so I got a wire here, magnetic field coming out. I got another wire sitting on top of it. Magnetic field will make 4 Tesla. And instead of our I, J, and K, I hat and J hat. So if I hat's to the right and J hat is up, which way is K hat in a right-handed coordinate system? Yep. And if you've forgotten, I hat cross J hat equals K hat. So I hat cross J hat gives us K hat coming out. Let's make the velocity equal to, of this wire right here, 5 meters per second I hat. And 2 meters by 3 meters. And I'm going to throw a resistor in here. What number have I not used yet? 6 ohm resistor, sitting right there. I assume that the wires are perfect and ideal and have no resistance whatsoever. Resistivity is 0. So, in the movable wire, what is the magnitude? Or, I guess I don't have to say magnitude. What is the current? And in which direction does it flow through the movable wire? Let's see, what is the current and in which direction does it flow? Now there's the straight plug and chug using the formula that we just derived right there, but we'll have to do one more thing after we've got this, because what is this telling us? What quantity would we solve if we just plugged into here?
Or epsilon.
Say again?
Epsilon? Or E, or whatever that represents.
Oh, yeah, the EMF. What is EMF? What units would it be?
Newtons? Well,
If you're stopping there, then no.
yeah, because it's not just.
Well, let's do it bit by bit. What are the units of magnetic field? Let's SI units of magnetic field. Okay, would be. All right, so we got Tesla times. Times. You didn't sound sure on that one. You feel like I'm setting you up for something?
Meters per second.
There, okay. So we're left with Tesla meters squared per second, which is, oh, let's do some fun with units.
Oh.
Someone has to know, find the answer quick.
It would have been easier if you knew what an EMF was. That would just really narrow it in. But let's do it this way. I know that F is equal to QVB, technically, V cross B. But since I'm only caring about units here, I'm going to drop the cross product. So the units of here would be a Newton. Units of charge?
Cool. Meters per second. And Tesla.
All right. So we can now narrow it down to Tesla. Tesla is a Newton second per Coulomb meter. Oh, this
Fun fact, or like we got that from somewhere?
we got. Say it again.
Did you just put that up there as like fun fact, this is equal to it, or did you get that from?
I got it from this equation right here. Because solve for Tesla, you multiply both sides by seconds and then divide by.
Oh, okay.
Oh,
Got it.
okay.
Yeah.
You didn't just, okay.
Yeah.
Yeah, no, this is not something I don't have this memorized. This is not
Okay,
straight from
okay, yeah, okay, I got you. That makes sense now.
Of course, now we'll be stuck for at least a day, but. Let's see, need some room here. Oh, look at the new picture over there. All right, so what I'm gonna take my Tesla and plug it into that equation right there, so my units of EMF become a Newton second meter squared per Coulomb meter second. So we can start narrowing some of this down.
Seconds can be
Get rid of
taken off.
seconds.
All right, so seconds go away, and
Get rid of 1 meters.
Yep, 1 meters
so I'm left with a Newton meter
per Coulomb.
per Coulomb. And what is a Newton meter?
Is that volt?
Oh,
If it's a Newton meter a volt? Is that what you're asking?
oh, man.
No, what is a Newton meter?
Yeah, what is a Newton meter? Or did you jump ahead and tell me what the units of EMF are?
Yeah, I was thinking that was those 3 right there, was volt.
It is your volt. What is a Newton meter?
Joule.
Yes. Say it again.
Joule.
There we go.
Energy.
Coulomb.
Yeah, joule per Coulomb. Because remember when we derived the electric potential, which is as the units of volts, we started with the energy formula and took out one of the charges by dividing by it. So joule per Coulomb is a volt. And EMF is just a voltage. That's what I was gonna save some time, but not as much fun that way. So the units of EMF is a volt. It is telling us it's an ideal voltage, ignoring, so if I have a power supply, if I ignore the internal resistance, and I measure the voltage, that is the EMF. Once you actually hook it up and have to take into account the internal resistance, what actually is the difference in potential between the two leads is slightly less than the ideal. All right, so let's figure out what is the EMF of our situation right here. Well, let's blend it.
Love it.
So 4 Tesla times my length, 2 meters, times my speed, 5 meters per second. Now there is an inherent assumption that the magnetic field is perpendicular to my loop.
I have a quick question.
Yep.
Why did we leave it at 5 meters per second? I thought for some reason that last part of the EMF formula involved our W, which in this case is 3 meters.
The last part was the rate at which W was changing. I still have it, delta W over delta T.
Okay.
W is that distance right there, and so the
Right.
rate at which that distance changes is the speed.
I see, okay, thank you.
Yep. And so therefore,
40 volts.
now, we have not answered the question yet, but this is probably the hardest part? Or is the hardest part for then get out, how do you find current now?
Is it that formula that also has resistance in it?
Yes,
Yeah.
The ohms.
yes.
We got it.
Um,
That is-
It's something equals something times something.
You are absolutely right.
One of them is an I, one of them is a V.
R, I,
Yeah.
is it
V
I
equals
equals R?
IR.
R, yeah.
Yeah.
God, I don't know.
Technically, delta
I
V,
forgot my
it's
notebook.
the voltage, not the potential itself.
Okay. Delta V equals IR.
But we're dealing with a nice ideal situation, so that delta V is just our EMF. And so we have 40 is equal to my current times the resistance, which I threw in there. Because my wires were perfect, the only resistance is coming from the resistor there. And doing the fancy math, 6.7 units.
Amps.
And then the direction that the current's gonna flow in the movable wire?
Down.
Yes.
Yes.
Because the velocity is in the positive direction in this, the way I've drawn it here, we were expanding the area, which means we're increasing the magnetic flux, which means that the induced current is gonna create a magnetic field to oppose that, oppose the change there. And again, right-hand rule, it's flowing clockwise.
So would we write that as negative J hat? Like the answer I would be 6.7 amperes negative J hat?
Be careful of that, because current still is not a vector, even though it does flow in a particular direction. It's not a vector quantity. So, if it were a vector, okay, perhaps a better reason for why it's not a vector quantity than what I've given in the past. We've talked about Kirchhoff's junction rule or current rule. If I have 3 amperes flowing in this way and 4 amperes flowing that way, what's the current in this middle branch?
Negative 1?
I don't know, what do you mean, negative 1?
Amperes? I was just,
Okay, I don't have a problem with, okay, amperes. What does the negative mean?
It's going,
I don't know. Well, I guess it's because what goes in must equal that which comes out.
Right?
So I chose negative 1 because 4 minus 1 is 3, and if 3 are going in, we want 3 going out. And 4 is greater than 3. So it seems like it should be negative.
So negative 1 going out,
I guess, I don't know.
or 1 going in?
Oh. Right, okay.
So 4 going in, 4 going out. If current were a vector, then I would have to take these directions to account. And so I'd have some in the I hat direction, some in the negative J hat direction, some in the I hat direction, it wouldn't work.
You're right, yeah.
I can't add those two if they were vectors and get that.
That makes sense.
That's why current is not a vector.
Hmm.
So just, it'd be a nitpick, it would be a minor deduction, but it would still probably be a deduction if you express the current as a vector itself. But so the current though we have is 6.6 repeating amperes, and then down, or you could write negative J hat, just writing them separately.
Hmm.
Questions up to here, because I'm about to change it slightly. All right. So the motional EMF, this voltage that we pick up from something moving through a magnetic field, we can also use this formula a little bit more generally than this type of case here. I have a bar that I'm going to drop. Now, I don't know which way the magnetic field officially flows at this point. Well, let's just assume that the magnetic field's flowing that way. So I have a metal bar here with a magnetic field coming out of the board. As the bar falls, think about, there's positive charges in there. Now the positive charges are not going to move sideways. Positive charges are going to fall with the bar. The negative charges are the ones actually going to move. So I guess the question really is, which way will the negative charges move? But you can think about it as, well, let me reword that. Ultimately, the question is, which way will the current flow in the bar? Now, you can go through several different mental gymnastics if you want to. If you think about it, which way would the positive charges be forced? That would be the direction that the current is going to flow. In reality, the negative charges are the ones that are gonna move, they'll move opposite direction of the current. But let's think about the positive charges in there. Which way are the positive charges forced as this bar falls through the magnetic field that's flowing that way?
Should we think of this as the area underneath the bar, between the bar and the ground, getting smaller?
No, see that, don't think of it in terms of area, just think in terms of what we did in the previous chapter. What was written up there. We talked about the force on moving charges. When we first did the right-hand rule.
So we point in the direction of movement and curl our fingers in the direction of the magnetic field and say that the positive charges are moving to the left?
So the positive charges are gonna be forced that way, or using the Sten gun. So positive charge is moving down, magnetic field coming out, thumb points that way. Which way will the negative charges move? Which way will the positive charges move? Ooh, no. Which way will the positive charges move? I did actually say it about 3 minutes ago, but that's the way they're forced. Which way will they move?
Oh, they don't move.
Not left or right. Now, if you want to be pedantic, and I was not intending when I first started it, but which way do the negative charges move? Negative charges actually move like that because there is a downward component,
Oh,
because the bar is falling. And so in that same respect, the positive charge is just moving down with the bar.
oh.
Which way is the current flowing in the bar? I assume there's a finger there. Okay,
This way.
Yep.
The left.
so I'm gonna have a current that is flowing off to the left. There's an EMF, that if I have a charge, if I have a current, there's gotta be a voltage. Charges, unless it's just some random coincidence that I drop this bar and somehow a current just magically starts flowing without it. So there's also an EMF between the two sides here. Now the charges will flow until it stops. That's a brilliant insight into life, that things will move until they stop moving. Charges will flow, and basically I'm gonna get a buildup of negative charges over here on this side, because the negative charge is really flowing. They will create an electric field that's pointing in that direction towards them. For the electric field, if I just set the bar there, the electric field in the bar is pretty much zero. It's evenly balanced. As the bar drops, negative charges will start to flow, creating an electric field flowing in that direction. And ultimately, it will keep doing that until the voltage at each end is roughly the same, when it's equipotential.
Wait, I'm sorry. The negative charges will continue to build on this side until the voltages are.
Until there's no potential difference between
Okay.
the force charges to move. Yeah, I'm gonna leave it vague like that. All right, let me leave it a little less vague. I start out with a neutral bar. I have an EMF that's induced. So I've artificially, or by dropping it through a magnetic field, I've created a potential difference using the motional EMF, using the formula blend. It does apply here, even though there we derived it using this change in magnetic flux, but it applies here too. So it starts out neutral, and as it falls, I'm gonna start getting electrons showing up over on this side. Presumably there's enough force to strip these outer electrons over. I'm not saying it's a huge current, I'm just saying that there is a current. When the charge shows up over there, we have now a net electric field pointing off to the right. The more charges that show up over here, the bigger that net electric field is pointing off that way. I know that there's a change of potential that's very much related to that electric field. So we start out, as it starts to drop, this is the low potential and this is the high potential. As the electrons build up over here, there is, my change in potential based upon this will be in the other direction. In other words, if my electric field is pointing off to the left, electric field points from high potential to low potential. And so we've got this electric field, because the bar is falling, because of this, because of bled. And then we'll have an electric field going in the other direction because of separation of charge.
How did we establish that the left was low potential and the right was high potential?
Because the current's gonna be flowing that way. The induced
Oh.
current will flow to the left.
Okay.
So we have these two competing factors here, both working, one is trying to make this side the low potential, the other one's making this the high side. At some point, it'll be balanced out and there won't be any charges flowing anymore. Questions to there? Okay. Chapter. All right. We've talked about resistors, we've talked about capacitors, and power supplies. Let's bring in the fourth component.
Wait, right before you introduce this, can